Alright, so this time, because we are gonna do the case statement for the cool compiler, we have to implement depth first search, and that's needed because when we are trying to perform the checks, we need to be able to check for the entire tree structure of classes. So in this example is the one that I just draw. We have the inheritance chain like A is the main class, and then we have B and C on this side, and on this side we have D and F. So if we do um, a DFS search, we are gonna get the classes in this order, right? So that would be the idea. We have like 0, 1, so on and so forth. We have the tags in the name table, right? Something like this. So if we take a look at how we are generating the tree address code for the case statement, we can see that it's gonna be first we check if is the object is instance of a class. If it is, we go to its label. Otherwise, we try again with the next class, with the next class, the next class, the last one. Right? We try all of them in a series. So what I think, although I'm not really sure, we can, I guess we can check that um, just to be sure, I guess. But I think the order of the statements is not really important. It's just that the closest one or something is selected. So it's pretty weird how this is done. So it means we can reorder them in whatever order we want in here. We are not really, let's say, forced to take the order that's shown, I guess. But that's also a bit man, I literally cannot see. Does the order matter in this one? I mean, I would say, like, for me, I would like the order to matter because you can have. But even then, if the order doesn't matter, then um, it's still fine. We can also take a look at the operational semantics. That's like for the interpreter. But in this one, I can see here closest ancestor. So it is like any order. I mean, if it is in any order, then I guess yeah, why not? So that means that we have all these classes with their number, with their tag. We already have the tag, but when we generate the triades code, I think that's something we have to change a bit. I mean, the instruction set will still be the same. I think it's good enough with this instance of. But I think yeah, I think it's still good enough to have easy instance of. Um, but I think we have to reorder in here the classes based on their position in the tree. Now in this example that I have here, they are already ordered. Like we start with C, then it's EFA object. So it's not really interesting there on that regard. They're already sorted. But yeah, we will have to keep that in mind to sort the checks here, right? That would be one thing. And the other one is how to actually implement this instance of. That's that could be more interesting. But if we are gonna do DFS on this thing, when we build the, I guess, the semantic mapping, then we should be good. That should be enough. So yeah, let's go to semantic.c, and here when we do semantic mapping, I just think that, okay, here we go through, so here we go through the context classes, here we go, after that we go through the mapping itself, right? We go through the mapping itself. So if here we set a specific order for the classes, this is gonna follow that order, this one as well. And I think, yeah, so all that we have to do is when we iterate through these classes, we do it in kind of a DFS order. So instead of just going through the context, we have to take the object class, like the main one, the parent of them all. We take it and do DFS on it, right? So let's do a function here, static void, and I guess it should build an array. Let's just keep it simple and build an array. Or we can build a queue, whatever you feel like. I mean, let's do a queue, why not? It's gonna be interesting to use a queue, right? We basically iterate the oh my god, the AST, not really the AST, but the context, right? So the context also contains, I think, I mean, yeah, it's the AST basically. So let's do I have no good name for it unless like it's DFS. Search DFS class 3. Okay, so we are gonna get here a semantic context, right? The program node. I have no idea if we need it. Let me check if this is. I guess it looks like it's used. Who knows? Okay, and as I said, we are gonna return, or like we are gonna have a reference to a linked list. Class Q, let's say. So something like this, right? And I guess, yeah, sure, we also need the current class, right? Should it be class node or class context? I think class context. Class CTX current. So it's class context, right? So it's like the current context. Okay. Alright, so now I think we can imagine that we already added this guy into the queue. So what we have to do is a for loop. Or I guess and we can try to say, okay, because we can add it either here or in the for loop, right? So it doesn't really matter. But let's say we push it here, then we have a for loop over all its children, so it's not really ctx. We actually need the program node, so like the class node, so we have to search for it. So let's go ahead and find a place where I do that. I guess it should be like find class node, and it takes in the program, the name, and the reference to that. So it should be a current context, name, and class. So here we need to go through class. Wait, I really thought that we had a tree of the inheritance, didn't we? I guess that's lame. I mean, I'm pretty sure we did some kind of... I guess this has the parent. Okay, anyway, let's do another function, static void search, or I guess find child, or like generate children, and it should get a semantic context. Context is the program node. Let's delete all this extra crap. The context itself and the ds dynamic array of children, which we are gonna modify. Okay. So how this is gonna work is we are gonna initialize the array, right, with class context. Then we kind of have to iterate, yeah, basically all of the classes. So unsigned int I. Can we use the context classes? I guess, yeah, we can use the context classes dot count I++. So here we need to take the current, yeah, the current, like the potential child class, and we need to check if the current's parent is the class that we provided as an argument. We have to check that if they are equal, and I think we can use pointer equals because they are going to be references. It's like a really big graph, right? Like the data structure that we have, I guess, in here is a reversed tree. So yeah, I guess that's why I remembered wrong that we have the tree already. But nonetheless, this is how we generate the children. So we don't really need this guy, right? We just need to create the dynamic array for the children. We generate the children, and now we can iterate over the children. So unsigned int I, we iterate the children, we get the child, and we run DFS on the child. So I think this should be enough, right, to generate the queue. So we add the node that we are on, then we generate its children, we do a for loop, and here we just add the child there. Yeah, it sounds good. I mean, it's not really a good idea because we are using recursive, and you never know how many classes someone will have. So maybe we should use a while loop. And I know that we already did something like that, right? So it shouldn't be that difficult to redo. But yeah, I mean, let's just leave it. Let's leave what to do here. To do, maybe do it iteratively, so it's a bit less annoying. So here we initialize this guy. So let's create this dynamic array. Well, a linked list. I wanted to say a linked list. The class queue, we have to initialize it, right? Class context root is gonna be object. Let's see. Yeah, it managed to figure that out. And now we have to do the search DFS. We start with the root, which is the object. We put everything in the class queue, and now we have to here do a while loop, but we still need the int. We don't need the int. Yeah, I guess we don't need the int. Okay, so let's remove all this stuff. Let's put this guy out, and let's do a while. I mean, we can use either linked list empty, which man, linked list empty returns 1 if the list is empty, 0 otherwise. And the other option would be to do either pop, one of the pops. So pop also returns the status. So we can do this linked list. So let's see, we did push back, so we can have pop front, right, like this. Oh, I mean, yeah, if we do it with empty, we have the object here, so let's do pop front. Doesn't really matter. I guess one extra thing I should do. No, not exactly. Okay, anyway, so in this, now we should have the classes in another order. So let's check if things still work. they shouldn't really work because we changed the order of the classes. So yeah, but interesting. I wonder why this happened. Well, it's a pretty easy way to figure out where we had the error, since we are using compile symbols in our main or in the project. It's easy to find the errors. So yeah, like a trick to have Valgrind show you the actual light line, you have to use compile symbols like -g with Clang or GCC. So 2090. So here, when we set the parents, so class context is gonna be null. Hmm. Yeah, let's see what was here before. It was just like go to the classes, nothing special. I mean, let me just printf the class name. Let's see, because I don't really remember what we had there. Right, so see, like it's all the classes, and yeah, this is what's nice about undo tree, is that you can actually have a real undo. Man, okay, so now what classes do we have here? If we take a look at the classes, they are cooked. Okay, probably because we pushed and popped differently. Let's see. So here we push the address to a class context, right? So we push the address. I guess, how does this guy work? Allocs, and it mem copies. Okay, so I mean, if we said here we are gonna use pointer to class context, I guess we actually have to use a pointer, because I can see that here we push back reference to a pointer. So here, but here we also do that. So what? So this gives us the reference. So okay, I guess. Like, this is the normal way of doing it, in my opinion. Yeah, here we get the reference again. Like, to me, it's the normal way of doing it. What if we try to do this instead? So here we have a void pointer item. What if we do this? didn't work at all. I guess, sure. Hmm. Okay, I mean, let's do like this, and then class context is gonna be the others to see or something, just so we can. I mean, I forgot to make. Okay, I really don't. So this gives us the context. That's fine. I mean, sure, it's a problem with what we add in the queue. That's the only issue. So we try to add this thing. Okay, let's go into ds.h. Let's see the queue example because I'm too dumb to think. Okay, so when we push back here, we said we're gonna have a list of int. So we push back an address, obviously, so it has to be a reference to this. Right, like if here we use class context pointer, we have to add wait 1 second. Okay, so here we passed in just a simple pointer. I mean, why not just use here class context like that? So here when we pass the pointer, it is current context, should be just a reference to it. Like in our example, right? We had int and we were pushing int pointers, and when we popped, we also popped like that. So I guess it should. But I mean, even that should have worked. Probably. Probably my thing is really scuffed. Like class by. Well, class object, at least that's good. So it means here we don't pass something correctly. So maybe when we generate the children, we do something stupid. So here we do dynamic array of addresses. So yeah, I guess here is actually the problem. So the queue was fine. right? Like the queue is fine, but generating the children is not. So here we said we are gonna have addresses, right? Here we take this thing, but if we want like address, I mean even this one is fine. Okay, let me just printf here the child name. Okay, so see, like the child name is not good. I know why, because wait, do I know why? No. Let's just move this into here and actually not use that function. Let's just keep it more simple. So here let's call this one child context. So this is gonna be child context. Not really, should be the other way around, like this. And instead of doing that, we can actually just recursively call here. So this should be child context. So now let's try to see here, printf the child. So if we don't use the array, I thought this should be better. Current, let's see the current context. Current is object. And if we do potential child, like what? Really? What? But how? How though? What's wrong with the context? Maybe, wait a second, like it's class context. How is it possible to get back null? Oh, because, yeah, because I cannot. Okay, yeah, I guess that was the mistake. Actually, probably in the, like, here I was using current context the whole time. Probably. But I mean, since we already changed it to like this, um, I think we can still keep it like this. But yeah, we can keep in mind that we can try to do it iteratively at some point. But yeah, so looks like in this thing it didn't change anything. But I was expecting maybe the test cases to not work anymore because but I mean the test cases are really simple, so they are not going to be influenced by changing the traversal of the ST. So I think that should work. So for example, if we go into 17 example, if here, I mean, won't change anything. So yeah, we just have to check this. Yeah, I mean, I really thought that if we do the assembly, if we take a look at the class name table, I mean, obviously they'll be in order of the ST. But what if we go into this one and actually put F here? Will it still be? I mean, I should have just ran make. Will they still be in order? Like F should be the last one. Well, I mean, they are in order. F comes after D, like that's what's important. So yeah, I guess the traversal works. Probably that it didn't affect anything in the like generating the errors or anything like that. Right, I guess it didn't affect generating the errors. But yeah, it should affect generating the assembly here. So I mean, here doesn't matter. But now we should go to, so wait, let's see. Yeah, we did the DFS here. So we just create the mapping using DFS traversal, I guess. Okay, so that's the first step, basically. Right, we just needed to do DFS here. Okay, and now I guess when we do, like, there should be a switch here. When we do the case, we should use that traversal at some extent to sort our cases. So that should be like, okay, let's sort the cases and we should sort them in the reverse order based on the ST. So like we go like this because this is the output of the DFS, right? A, B, C, D, F. And if we go in the reverse order, it should give us the least generic one first and the most generic one last. So object would be last, basically. Okay, so let's see how we can do that. So here we have cases. Do we get a context here? We get the DAC context. Does the context have a dynamic array mapping? When we do expression to TAC, we just get a node expression. Interesting. Should we maybe also require the semantic mapping? Like the semantic mapping would help with that order, right? So I guess we should probably. So let's go to this thing. Semantic mapping. Let's say it's gonna be like context. But like we already have a context here, so maybe let's just but I guess the context is used for what? Ah, okay, so we can actually put the mapping inside of the context. Then if we pass it, so let's just say mapping. Oh, I thought I ran the code action one. Okay, yeah. So semantic mapping is gonna be mapping, and yeah, I guess here we can do mapping is equal to mapping. Ah, we already have mapping. Um, which is used for what? Assign value. Okay. I mean, let's do like this. Okay, so now we have inside of the context we have that semantic mapping. So now if we go to case, well, it's case. Am I really blind? Okay, it's expression case. Okay, sure. So here, yeah, we should order the cases by the by the classes. Okay. So I mean, yeah, let's just try to do that. Okay, I guess cases is a dynamic array. Yeah. Would be nice to have a function for sorting on the dynamic array, like in the ds.h library. And you specify like a function. Yeah, like how to sort them. I guess would be fun to have. We already have swap. So let's try to do it here. Why not? Yes, dynamic array, because it's gonna be like two things at once. So we are gonna have sort and the compare function between two elements. We already have swap, which is Okay, so I want to put it, I guess, here. Now the annoying thing is that, well, we can try to yeah, just do it in ds.h. ds.h, ds dynamic array. So if we go to, I just didn't have LSP, or at least it's black and white, I don't know, because it's like Clang doesn't really get that I'm including this file in the source code. So um, let's put it like this, and yeah, let's try and do it. So it's gonna be probably just calling to qsort, yeah. Let me see if it's right. So it's the items, which should be a pointer, yeah. The number of members, which is count, item size, and compare. Yeah, I think it should be fine. Oh, and it actually returns void, I guess. So this can be void. Okay, then yeah. So I can just overwrite it. Okay, yeah, yeah, it's fine. So if we go back to uh, what was it? CodeGen, right? CodeGen. We can try to say something like dynamic array sort. Yeah, like this is gonna be the compare. But the compare sucks because it also needs the context, and you cannot have I guess partial functions in C, or like methods and stuff, so it won't work, I guess. So then yeah, we just have to make it manually to some extent. So the other option would be to just yeah, I mean, I don't really want to implement the sorting. It would really suck to do that. So the other option is to iterate the classes in the context, check if a case matches with that, and if it matches, then you do this thing. Right? But we have a lot of for loops. See, like that would. Okay, I mean, let's use a queue again, maybe. So we're gonna have a for loop. So it's gonna be similar to the one from the semantic, well, semantic.c. Like have a queue. Maybe it can work. ds linked list init. Okay, nice. And yeah, now I will just unsigned int is equal to 0. I will just go to all the classes. Okay, we have a semantic mapping item here, so we need to get a ref. This should be a void pointer. Okay. Although I also said it should be in the reverse order, right? So let's just, I mean, minus this guy. So if we have, we also need -1. Okay. And I guess it's not ideal to have another for loop, but it is what it is here. So we iterate with J on this one. I guess let's not do a linked list because we're gonna lose the stuff. So let's do a dynamic array. Case like branches. So initialize it. Wait, is this branch node? It is branch node, so it's good. So here, if I think should be something like this. Yeah. Do we do anything else with case after this point? Except case, get cases? I mean, I guess we would just need to sort the indices or something, but I mean it is still good. Okay, so we don't. Yeah, we don't really do anything with case afterwards. I mean, yeah, let's just keep indices. Let's just keep the indices of like the J's, I guess. So if we don't have a name, it should be like class name. Okay, yeah, it's class name. So if I would rename this to item then. And I guess this guy is not right, so let's do a branch node, let's get the ref. No idea why it tries to do it like that. I mean, it has an example what's 5 lines above it. So branch type value. And if that's equal, then we can add J to indices. So all in all, we still sorted the array, but with 2 for loops instead of qsort. I guess it's fine. Right, I would say it's fine. So now here we are gonna loop through indices count. Maybe we can also assert that these things are, we don't have an assert in our, okay, whatever, it's like, it's gonna crash, right, if they are not equal. Maybe we have a bug or something in this logic, but they should be equal. Okay, so we have indices count. Let's maybe use j for this, and then let's have int I, and let's just get the value. That should work. Let me just printf I, and this should be copied, copy pasted there. Because yeah, we do something like, here we create the check for the case, like for all of them, and then we create the body of the case. Okay, so let's just see where we have some errors. So in assembler, that's the first one, assembler.c. I guess we should pass the context mapping, but I'm pretty sure we have some more. Expression to TAC. So in print TAC. Like here we should provide a mapping, and this guy should get a mapping. Antique mapping. Cogen.h. So this should. Okay, I mean the name is not right. Okay, let's see some other errors. Probably in main. Yeah. So here we need to pass in the mapping. Now there is the mapping. Yeah. Okay. So if we take a look, well, I just wanted the three others code, I guess. So the order is from the list is FCA object, okay. 17 example. So I guess it looks good. Right, the order is fine now. So that's another step closer. So let's see. Yeah, here we modified quite a lot of stuff, but it's like it's just reordering these guys, the cases in the triadic code generation. Okay. So this was just printing. This was just passing the mapping. This can stay. And this was also, okay, so feature order the cases, branches, or whatever. And yeah, I mean, update the sh. So I guess now we can go to each instance actually, because now we have the cases in order, we have all the classes in order. So I would also expect, let me see, that if we try to look at the assembly, we are gonna see the class name table, where is it, in the right order. And I guess it looks in the right order. F and E, yeah, it looks in the right order. So I guess we are probably ready to I press delete on source. I guess we are ready to tackle the last to do. Compare the tags, but first to do semantic mapping. Okay. So for easy instance, right? What I tried to do here was complete BS, I guess. So let's just I guess let's just delete this entire stuff. And casting, we don't even need casting, but yeah, because the type of an object won't change regardless if it's you know like it matches with a branch, it's not gonna be casted to anything. Like I think that's just useless. I mean, it's just loading the variable or something, but yeah, not needed, I guess. But now comes the interesting part, I guess, doing the easy instance. So to check if, let's say we have an object, and we want to check if it's, I don't know, instance of A, we just have to go from the, I guess from here to, yeah, I'm not sure if up until like the end of everything. It should be like between the start of the chain and the last class that inherits from A. But since we traversed it in DFS order, they'll be like right next to each other. They'll be chunked in a small chunk. So I think that's the way to do it. And for example, let's say we want to look at B, right? This is a good example. B starts right here and ends right here. So we have to check this chunk. So again, how are we gonna check that? We have the tags in the prototype object, so we can check the tags. And that's pretty much everything we have to do. We have to check if the tag is greater than the B and smaller than the C. And that's when it falls into the B category. Then for C, for example, we have to check that it's greater than 2 but smaller than 2. And then when it's falls into the C category. And this is for D. E is also only a single one. And A contains everything in this example, see, like everything. So that's why we have to start from the last one, because the last one is gonna be the smallest. Like F is only for F. So let's see now. Um, yeah, I guess that's what we have to compare the tags, right? It's gonna be a bit scuffed. I just want to see the tree address code again. I'm just thinking, yeah, I don't know. Yeah, like this is a bit useless, but it doesn't matter. Maybe it's gonna be used like to point to the right. Like if we go to 17 example, and this is gonna be like A, let's say. It's still I guess I renamed it. I guess that's really good. I'm a bit surprised. But yeah, I mean, I really thought ahead. Maybe? Question mark. So yeah, I'm really not sure how I want to implement it. If I want to change the tree address code to be more specific with what is instance of means, but I feel like it would be uh, too annoying to do. So this looks good then. So what we have to do, as I said, is to compare the tags. And we have to compare the tags. So here we know which is the current class that we want to check. Right, it's gonna be given in TAC is instance. We are gonna have the type. So we can search for that thing in the semantic context. Right, you can search for it. And I guess is that gonna represent something like the start or the end? I guess it could be the start, but then we would need all its children to figure out which is the end. Right, we still need to get all the children. So if we go to semantic.c, to get the children we were just doing this. Oh, but we need like all of them. We don't really need to keep track of them. We just need the index, like the class tag of the last one. Like, we just need the name of the last one, the last child. So, yeah, probably we are gonna reuse this method then. DFS. We are probably gonna reuse this one, right? Um, so on what I was just thinking where it would make more sense to keep it in semantic search. I guess that's where we are. So although the issue is that it requires the semantic context to run. But we don't have it. Yeah. So yeah, I mean, I guess we can just try to copy paste this function and try to use it. Yeah. Let's see another option to do it. So this should be semantic mapping, probably. Like mapping. Okay. And this in the mapping we have semantic mapping item. So we can store that in the list, basically is what I'm trying to say. Or what I meant is this is what we are gonna store. So this should be current item. Current item. And I guess it doesn't really matter if it's a linked list or whatever, because we are gonna need just the first item and the last item. So yeah, that's what I'm thinking. So now we should go through the mapping and let's go through the classes. The idea is they'll be in order, I guess. At the same time, we just needed the index, so I don't know how we can maybe not even worry about having to do this entire thing. And maybe there's a better way. Like for example, you pass in an index and you search for the next node that has the same parent as you, and that is the end index, I guess. I guess that makes sense. So unsigned, or maybe size the index, and we are gonna output a size t and index, and let's call it start index, right? CS, okay, size t. So here we need semantic mapping item, the current item, right? And now let's make a for loop from size ti from start index up until the end, obviously. We also need to get this item, and let's say semantic mapping item parent is gonna be null, right? I mean, obviously it's gonna be the item parent. I don't know why I said yeah, it's null. Okay, it's gonna be the item parent. Okay, here at the end I would say end index is gonna be equal to I, right? So we take the current item, and if, let's see, yeah, no, it should be if current parent is equal to parent, then we have to break. Let's see. Okay, so we have to start from start index plus 1, I guess. And end index should be by default, and index should be equal to start index. And we start from start index plus 1, right? And if the next node parent is like this, no, find case range, I don't know, then we should just break, my friend. Okay, yeah, so the idea is, since we have all the classes in order, let's say we start with B, right? We have start index on 1, end index is also 1. We go on C. Does C have the same parent as B? No, then end index becomes 2. Then we get to D and check, does D have the same parent as B? And the answer is yes, so we stop. So that's where we get 1 and 2. And yeah, I think pretty nice algorithm I came up with. It's too neat to work. Okay, so we have the start index, which is gonna be taken from the class, like the name table. Yeah. So let's see if we have a way to do that. I guess the way to do it is just, go ahead and do that. So yeah, we have to iterate all the classes, and when we find the one that has instruction type equal to class name, we stop. And that's the index, because the classes are in the same order as the name table, right? So we actually have them in the right order. So then we just have to get the end index, right? And this crap, I think it can be just just inlined. I don't think we need a function for it. So this is gonna be context. Okay. Where is the index? I lost the end index. So size the end index, context, like this, and yeah, it should be good. Okay, perfect. So now we have printf the start and end indices. So if we remake this thing and what the fuck? It's funny that it's like, yeah. I don't know where I got these two from. So printf case what? Printf. Oh, I forgot this one in CodeGen. Interesting. So okay. So let's see now what the values are gonna be in this thing. I still see the case. Okay. So we have start is 5 and this is for a boolean end, so it doesn't really affect us. But I'm curious to see in what the method. Okay, so we have start 11 and end 11, 10 and 10, 8 and 11, 6 and 10. So let's go to the 17 example. So we have C, which is one of the last classes, I guess, right, in my drawing. Yeah, that's why it's like 11. Then 10 is which class? It's like E. But then for F, it goes up until 11. Like what? Why though? 8 to 11. Then interesting for oh, I guess no, no, no. Yeah, I don't get why it's like that. Maybe I was wrong and it should be breadth first search. No, doesn't make sense to have breadth first search. It has to be depth first. But then why does... So it's gonna be like D, E, and F. So why does F look like that? Yeah, maybe my algorithm wasn't really that smart then. Well, I mean, I tried, but I guess wasn't good. I would really like to know which classes these are though. So let's try to at least print that also. So do we have, I guess we have at least start, semantic mapping item, and so we can actually just print the names because it's easier to see. So it's item and end. So let's take a look at the method. So it's gonna be start E and E. That's kind of okay. F and F, and then it's C and E. So it's gonna take C, and since C is the last child of B, it's not really gonna have a next child that can check against the parent. So yeah, we should check in some other way, in some other method, um, that this should be the end basically, and then it's from A to E, which is nice. It's like all of them. Object to E. So yeah, when we compute the end, we should do it in a bit of a different way. Let's think about it. Yeah. So how can we do it? We have the current item. We should check. I mean, it's gonna be a similar check to the one that we did in check inheritance. Like let's say we chose C and the next item is D, so we have to check that they have a common parent. If they have a common parent, then we stop. Right? That means that that if we have to go to D, then yeah, it's not ancestors of C basically, or it's not inheritors of C. It's not children of C. So let's go like up the chain for both of them. So in parser.c in Harry. I thought I had a function here like check inheritance or something. Oh, it's not in parser. It should be in semantic search. So it should be here like inheritance. No, ancestor. Yeah, basically ancestor. So, but we just need the while loop. We don't need anything else. Like the self type is taken care of, I think. So yeah, I don't think we need anything else. So probably we are gonna need something like this, right? So we have the current item. We also have the item, right? So what we actually need to do, probably we are gonna need an int found is equal to 0, and if found, then we have to break like this. So let's say we have current, so we can change that. So let's do a do while loop. While current is not equal to null, right? That's the only thing that can happen. Well, yeah, but this is not enough. We need a list. It was something like list common ancestor. I think this is what we need. So we need like 2 while loops. Okay, I mean, I guess it is what it is. So we have a while loop current is not null. Current is equal to current.parent, and yeah, here we should do a do while loop. Or I guess I mean I can also do semantic mapping item, like a copy of item, you know. Let's say tmp is equal to item, and we have to do a while loop again. So while tmp is not a null, if tmp's name is equal to class name, we found something. So here we can do something like if found we break. It's really ugly, but hopefully it does the job. Let's see. Oh no, it didn't do the job. Damn it. So yeah, it didn't work. I mean, probably it just found. Huh. Yeah, no, I'm a. So I guess. No, I guess what we have to do is just check that the current is a child of item. Like, that's all we have to do. Let's stop with this useless checking, and we have to just check if okay, so let's imagine it, right? Let's imagine how it works. So let's say we are gonna we try to look for the C node, right? And we found D. So D will go up and it won't find B. So find will be 0. But for E, for example, if we are on on E and we go to F, we will actually not find, so it's also like that. But if we are on D and we check F, it's gonna find it. Okay, so found is equal to 1, and I think we actually need to check if found is equal to 0. Let's see. Makes sense to me. So yeah, now it looks good. Start is E, start is E, C, A and E. Yeah, it looks good. Okay. Yeah, because we just need to check that um, current is a child of this thing. That's when we increase the index. So all in all, we still did the DFS thingy. But I think it should work. So I think it looks good to me. Yeah. So now what we actually have to do is do the two checks. So let's see how we are gonna do that. So we have start index, end index. I guess we just need to create a new variable, a new boolean. Like that's the first step. So like something like t0 is equal to new boolean. Let's see. We create a new boolean. Then we need to take get size of expression. So it's something like assembler get attribute, but this is not really gonna work because the attribute is just so we just need to get the variable assembler emit load variable. So we need the variable. Right now in the A register we have the variable identifier and we need to get the size of it. So that means we can look at attribute. How I did there. So here I think I got a variable and then I did something like this. Right. So something like this. So get size. So here should be inster expression. Do we have something like size? Assembler.h. Like when I want it to prelude.assembly obj size or obj tag. I haven't used that. Interesting. Yeah, but I mean we know that that define object size offset is gonna be at what, at 8? Yeah, it's at 8 because we use this guy. So here it's object size offset, right? Let's create a variable for a comment. It's gonna be null. Okay, so we actually load, well, I guess, yeah, right, we load the size into, let's say something like size of, get the size of the object, okay, into RAX. So now we have to compare, so something like, why the fuck I want to get the size? I want the tag. Define object tag offset. Yeah, I don't know why I thought about the object tag offset. Okay, so now we have to compare if start index is more or equal than tag or this, right? So how are we gonna do that? I think with two compares. So let's see. How can we do that? So we have, can't we just do, I'm curious to see what this guy did. So yeah, it's not what I wanted. Okay, so what I want to actually do is load the two things. Well, I guess we don't even need to load them. We can do immediate comparisons, right? Like we can do compare with an immediate. Let's check. Um, assembly compare with immediate value. Wow, trying to move the windows. Okay, so it's possible, so perfect. Then assembler emit fmt. We need to compare with this thing, right? We need to compare with that. Let's say we are gonna keep so the next thing to do is to set but I don't want to overwrite RAX. Then let's do another. Let's move into into RDI. and let's use RDI as the thing. So set greater or equal to the AL register. So let's have the first comparison basically, and we move it into racks. Okay, and then we have tag is smaller than this guy, so it should be it's stupid, but it won't work. Really. So I would say that's not really good. So yeah, basically we load into RDI the tag, right? Then we have to compare this thing and we store it into RAX, but here we overwrite RAX. So what if we move into and also use RSI for this one? RSI. Okay, I mean, whatever, we use multiple registers, it is what it is, RAX. Okay, so we have these two, and we want to set this as the value. So first we want to end the two conditions, and then we want to store the variable. Okay, I think this looks like everything, to be honest, for easy instance of. We create a boolean, so should be good. Let's just take a look if we have any weird prints in it or no. So here we get a tag, we check with RDI is greater or equal than 11 and smaller than equal than 11, and we store this, we jump to L1. I think it looks good, so let's actually try to, I just run the checker straight up and see what happens. It failed. So let's see. So this is the OP one. What? Excuse me. Oh, 15 op.cl. Okay, so I just wanted to see what happens with the random test case. Okay, so it runs, right? Let's see the simple case, because we have a simple one. So with the 6 segmentation fault. At least, I guess at least assembly 09 is pretty simple. Right, it's pretty simple. And it's not, to be honest. So where we create a boolean. Oh, we didn't store the boolean though. Store variable. Yeah, we didn't store the boolean. What? This just creates it into the A register. So we didn't save it then, I guess. But that's not enough though. it looks like it's not enough. I mean, why not just... Let's take a look. Let's just, step a few times. Let's breakpoint this bad boy, and let's step. Actually, I mean, yeah, I could as well just continue to the next failure. I mean, let's continue until we get segmentation fault, and let's see where it happened first. So somewhere we tried... It's somewhere where we use test. That's interesting. So it's in is void. Although we don't even do is void. What? Or in jump if true. Is it in jump if true? No, because it is a jump not equal after it. So it looks like it's some code from our prelude assembly then. It comes a jump not equal. What? But we don't even have jump not equal after a test. Am I wrong with something? Yeah, we don't have a jump not equal. Okay, I mean, let's start again. Let's see where it will happen. So here we just do the usual. Here we call to RDI. So 09 case. No idea what happens here, but let's just go with it. I mean, this looks like creating some variable, so let's just skip it. Okay, so this is for the case statement, right? I can figure it out that it's for the case. So we take a look, we move. So it might be the first one, right? With adding x plus x. So that's why we see there type 4. And I think if we make this guy and look at the name table, it looks like 0, 1, 2, 3, 4. Int is 4. So it's good. First we compare with 5. For some reason we compare with 5. I guess boolean is first in my thing. So 0, 0, and then, so it's false. We move whatever stuff around, and here is the jump not equal. What? So after we did yeah, something's Something's off about this. Oh my god, I forgot where I was, so it's in easy instance. So here at the end we oh no, we stored the variable. I mean, what the fuck? We need to set the attribute, like bruv. I mean, that's why you have to not rely on ChatGPT. So it's 001. I mean, let's run the checker. I'm not gonna check that. Didn't work. Zero 09. Okay. Let's see the ref. So it's 15. So it thought that my int is a string. How dare you? 001. Hmm. Hmm. Really questionable. Oh. I mean, we can still look at this thing even though it's wrong. But jump not 0. Well, how does it get to the string twice? And what's even funnier is that when it was actually a string, like on the third case, it didn't go to string. What? I mean, let's GTB the thing again, I guess. I mean, this time it's no longer gonna segmentation fault, so at least we know that something's working. So here when we do call RDI, we go into the method, right? Uh, create some variable. I have no idea what the variable is, but I mean, can we guess what the variable is? Oh, it's probably the boolean that we made for the thing. So here we compare with 5, which I saw it's for I mean, let's run this again. Name. Okay, I mean, if you don't want to show me, don't show me. Okay, so name table. Right. First is 0, 1, 2, 3, 4, 5. So yeah, it just likes to put the boolean first for some reason. So it checks that, but it's gonna be false. It does whatever with the t0 variable, sets it. Okay, so we load the boolean, we load its value, we test it, jump is not taken, so we try again. So we move the prototype, we create another boolean object here, which I guess it's understandable. Now we have to compare with 4. So and this is the number at the RBX plus 10. Right, so we move into RDI array X and it's 4 for some reason. What? Oh, because it's an int. Nice. So this thing should be true, right? This thing should be true. right? So we are gonna actually jump. Wow, nice. So it jumps to the end and that's it. Um, what? Well, my bad, my bad. Let's see again. So this should not jump, okay. And this time it should jump. Did I forgot to also reorder the branch expressions themselves? Like that would be funny. I think I probably I forgot to reorder the branches themselves. So like here for example, we move something into array X, which is a 4. Like that's the argument, right? That's the argument. Just because we needed the argument there. Then we move the prototype object, like the constant actually, I can see. Then we take its value, or what? We store the variable. We don't even take its value. So let's take a look at what this piece of crap is. Let's see. Right. I said that I'm gonna learn how to use this inspect thing, and so it has a 4. It has size 4. This is the dispatch table, and this is the value. So yeah, it looks like I forgot to actually swap the cases. So that should happen in CodeGen though. So here we sorted the indices, right? So this gives us the whatever, the branch shift through whatever, and here the body. Let's take a look at the tree address code. So if it is instance of boolean, jump to L1. It's funny, all the labels are. What the hell am I doing? Ooh, freak. Okay, what, Jesus. What is the mistake? So it looks like these are sorted, right? And the labels are gonna be also sorted. But I guess I'm indexing the labels wrong somehow. So when I take the case label, I think I should use J here, because here when I generate the labels, I just append them. So here I think I should use J. But to get the actual implementation, I might have to use I. So label 1 is when it's boolean, label 2 is when it's int. Okay, yeah, I think that's the thing that I missed. Like I should have, because here we just append the jump if true but also the label. Where is it? Here. So we create a new label and we just append it regardless of the order, and we do all this stuff in this order. So then we go again, and when we take the label we have to take it in the order that we placed it, so the J order, that's the case label. But the body should be taken, I think, in the I order, or it's still J order? No, it's I order, right? Because it's sorted. I guess that's it. Then 09 still fails though. 010. So it's still scuffed somehow from this thing. So let's take a look step by step what happens here, because I just did it. Maybe I did something wrong. So we iterate over J. We take the I index, so the order in which we actually should have performed the thing. So we create a new variable, a new label. We append the label in this order, so in the J order. Right? We get the branch node we do an easy instance. We append that to the list of instructions because we don't have an option, or at least that's the order we want to do it. And also the jump to the label. So then we iterate again over this. We take the index. We take the label from J because that's the order it was added. We create a case label. The body we take it from the I index. Then we add the cast, which is, I said, useless. Then we append it and add a jump done. Yeah, it looks like it's like everything is in the right order. Yeah, pretty strange. You can take another look at the tree address code, see if it's really good. So if it's boolean, it's gonna jump to L1, and L1 it means that it's gonna print a 1. Is that what we want? Yeah. If it's int, it's gonna jump to L2. So where is L2? Here. So it's gonna take the X. So that's good. If it's string, it's gonna jump to L3. So it's gonna take, here it's, I said it's gonna take T5, which is like, I guess, Wait, what? There is something wrong with that. D8, D9. Is something wrong here? And for object it happens like that. So I don't get what can be wrong in here. It uses T5 instead of T7. Right, like that's what I'm seeing. And it doesn't make any sense. Like if I try to do, no, I'll do just I equal J, just to make it do what it did before. So if I do this thing and we look at label 1, here is fine now. So it means we need to switch something else also. So here I made a variable for the identifier, which I don't know what it means, so we have to see. So identifier is the for the condition. This is the label where we jump. We create this thing and the branch if true. So yeah, that's good. Here we get a label, we put a label, and here for the body I said that we want the I branch, and here for the cast, let's see. Expression, where does expression come from? Where does the expression come from? So it's okay, and branch ident is gonna be a new variable. Okay, I mean that's kind of fine. What the actual hell? Bro, I mean, Jesus. How is it so overcomplicated? Bro, I swear I am, man. Because, yeah, I mean, here we take index I, the identifier, the case label, we create a new variable, like a branch identifier. Right, let's see. So this should be the only one that has a different order in its execution, the first for loop, right? So this is the only place where we are gonna need this I thing. In the other place, not sure how we are gonna use it, probably just for the labels. So we do the for loop, right? We create a new variable for the result of this instance, the label where we are gonna jump. We append the label in order, so it's gonna be L1, L2 in our list. It's not gonna depend on I, basically, is what I'm trying to say. The label is gonna be in order. Okay, right, it's gonna be in order, like in the normal order. Okay, get that. Then we create the instructions and the jump if true. Okay, so now when we go to the next thing, we are gonna need to take the label. Like what if we use I to take the label? So that means, let's say here I was 5 but J was 0, so it's gonna be first. So I'm thinking, if we take the label from I, right? If we take the label from, it doesn't make any sense. Like here we place the label at J for the instruction at I. So we took the, yeah, it's annoying that we cannot put the values in order inside of this label. But yeah, let's go further. So we take index I. Here we take the first label, right? That makes sense. Take the first label, like label 0, for example. So everything up until this point is good. Here we need to take the same branch as we did here, which is I, right? And that's good. Okay, I mean that looks good. So we need a new variable for the branch identifier, right? Then we do the cast thing. So that's like this. T5 is equal to that. T6 is equal to this. T8 is equal to this. T10 is equal to this. Right, but this was, I mean, the simple way of doing it. If we try to run it again, and we use our order, it's going to be T5 is equal to this, T7, T8, and T10. Right, like this. These are the variables. So, branch identifier. We created a new branch identifier. The identifier is going to be just that. The expression is the expression. So like it looks good, right? This thing, creating the variable, it looks good. Hmm? and it looks decent, so we add that. But then we have to do expression. Like, we need to do another expression. For this is just x, so the expression is just x. So why the fuck does that happen? So this is the cast expression, the cast instruction, which is branch ident. Then we have an assign to branch name value. Wait, what? Branch name value and branch ident. What? Wait, what? I guess. No, no, no. I guess here we said that. Oh, I guess, yeah. Oh my god, sucks. Here we said that we assign to our T5 or what? This is X and this is T5, right? So we said that T5 is assigned to X. But when we use this mapping, we should use it in the reverse order. So it's the tag identify which uses it. Mapping count minus 1 minus I. Because each time we add something to this thing, we actually overwrite its value. It's like we shadow it, right? Like, let's see now what happens if we take a look at the tree address code. So here it's fine using T7. Okay, and if we run this back, oh my god, it works. It actually works, even on the last one. But it doesn't work on 16, though. I wonder why. So it's 16. So it should be the sum, so 15. Then it's a boolean, so it's 1. Then it's hello, so it's 0, it's a string. Then it's new B, and new B inherits from A. So it should be 2. Right, it should be 2 and 3. Why is it, or I haven't put a test case for it, or what? 16 case, oh, I haven't done. 16 case more ref. Yeah, but this is the right output. I mean, this was the good enough test, I guess, for it. Oh my god, so yeah, we actually managed to do it. We fixed the case. Let's do the test cases, just the test cases. Jesus, that was rough. I mean, bro, how are you supposed to figure out that you have a bug in here? Like at least I guess I figured that out. Yeah, I mean the first one, the first ugly bug was here, putting, but I mean that was I guess a nice bug because we saw it easily, right? Like the order of the labels was like random. It wasn't L1, L2, L3, L4. It was all over the place. So this was easy to see. But this one, man, I totally forgot that I had that mapping between, like, today I saw that I had some kind of mapping because we were using the like the right values in here, right? Somehow we were always using X. So I knew I had a mapping, but I completely forgot that I used it in the case. I mean, where else where else do I use it? Just in the case. So yeah, that was nasty. But yeah, I guess in this one we just did, yeah, we just did this. Okay, so yeah, I guess that's all. Implement case. Yeah, I think that's probably all for cases. Now we are actually able to run more complicated code, but we still have to do equals. So I mean, this was the last one. That was like internal thing. So features, the equality. So equality is like a method. Like we can actually call it as a method, but we have to implement it in assembly because we need mem compare and stuff. Then there are like exception handling for when you do something stupid, right? And and I don't know, I was thinking to copy more test cases from other projects. It depends, right? And I really have this idea of maybe trying to have like a Linux class where we can have syscalls, and maybe that will allow us to extend the language a bit. Yeah, I guess so. Like maybe being able to add some graphics to it, but I don't know. Like that could be cool, right? So yeah, I guess like as part of the C code itself, I think we are pretty much done. Unless we, I don't know, unless, yeah, I'm really curious though. Clock, yeah, how do you use this thing? Hmm. Wait, it's install. Also, it's like available for like, can I do like clock dot? Jesus, 5,000 lines of code. I don't know where it gets like OpenCL from. Yeah, I mean it's pretty big though. Like the assembler has like 1,000 lines, but I think the humongous one is semantic. Huge. CodeGen was pretty small though. Yeah, but changes did I make in main? Just comments, yeah, whatever. But yeah, it's pretty nice. We just have the equal left to do, and even the hardest test works. So yeah, so is it 17 the hardest one? I guess so. But yeah, we get the right result. So we'll just have to implement the equals, and after that, yeah, I don't know. Maybe we'll try to extend the language a bit with some stuff, and probably do. I mean, I'll just do the exception handling on my own because it's not really interesting, I think. But yeah, we'll do equal next, like finally finish it, and I'll think about how to use syscalls because that will be quite useful. And yeah, I mean, I guess that's all for today. So see you in the next one.